In the 0 1 knapsack problem, we have a knapsack of fixed capacity. We have n items, each with a weight and value. We have to keep items in such a way that the value of the kept items is maximized. Since the knapsack has a fixed weight capacity, the sum of the weights of the kept items must not be greater than the capacity of the knapsack. In the previous video, we explained that the 0 1 knapsack problem is hard to solve. Even we can observe this intuitively. There are n items. A binary decision is associated with each item, that is, we can keep the item or we can leave the item. Since there are n items, the total possible solutions are 2 to the power n. One of the possible ways to find the optimal solution is an exhaustive search, that is, exploring each solution in order to find the optimal solution. For example, if n equals 10, we have to explore 2 to the power 10 solutions, that is 1024 solutions. But as the n increases, the number of solutions to explore in an exhaustive approach exponentially increases. For example, consider n equals 46. Let us consider checking whether a solution is feasible or infeasible, and if it is feasible, then the value obtained from the solution is one operation, and one operation takes 1 nanosecond. It will take 16 days to explore 2 to the power 46 possible solutions. If we increase the item only by 9, that is n equals 55, it will take 512 days to explore all possible solutions to find the optimal one. What if we don't have that much time? We need results quickly. Since we don't have time, we have to adjust with the solution. One possible way is to take a random solution, but we cannot comment on the solution. Therefore, we apply some heuristics to generate solutions. The greedy approach is one approach that gives the solution based on the used heuristic in a very short time compared to the exhaustive approach, but does not guarantee the optimal solution. In a greedy approach, we select the item that seems best at the moment. In the greedy approach, an important point to note is that we need some criteria based on which we can compare two items and decide the best among the two. There are two parameters associated with each item in the knapsack problem: weight and value. These two parameters can be used to compare two items. Let's discuss both parameters. If we consider weight, we can give preference to items with lower weight so that more items can be kept in the knapsack. If we consider value, we can give preference to items with high value so that the most valuable items are kept in the knapsack first. In both approaches, we consider only one parameter. However, both parameters are important. Weight must be considered in selection because the solution needs to satisfy the capacity constraints, and value needs to be considered because ultimately we are maximizing the value of the knapsack after keeping the items. Since both are important, what if we design some function that considers both the weight and value of each item, and based on the value of the function, we decide which item we have to pick to keep in the knapsack? A possible function is the ratio of value and weight that calculates how much value we get from each unit of weight for each item. It is also termed as efficiency. So, finally, we have three possible ways to design a greedy approach for the 0 1 knapsack problem. Let's design the first greedy approach considering value. There are two steps in this approach, or we can say there are two steps in this algorithm. In the first step, we sort items by value in descending order. In the second step, we keep items in the order obtained from the first step until the sum of the weights of the kept items in the knapsack is less than the weight capacity of the knapsack. We have a knapsack, and the weight capacity of the knapsack is 6. There are 5 items. The first item has a weight of 1 and a value of 1. The second item has a weight of 4 and a value of 4. The third item has a weight of 2 and a value of 3. The fourth item has a weight of 4 and a value of 5. The last item has a weight of 5 and a value of 6. In this approach, value decides the preference of items. The value of the first item is 1. The value of the second item is 4. The value of the third item is 3. The value of the fourth item is 5. The value of the last item is 6. The item with the highest value is the fifth item. It should be given the highest preference. After this, the fourth item, then the second item, then the third item, and the first item is at the last in the preference. Let's sort the elements in the descending order of the value. At this stage, We have the items in descending order based on their values. Step 1 of the algorithm is complete. Let's consider the first item, an item with the highest value. Since its weight is less than the weight capacity of the knapsack, we can keep this item in the knapsack. Now the weight capacity of the knapsack is 1. Let's try the second item in the order. Since its weight is more than the weight capacity of the knapsack, we cannot keep in the knapsack. Let's try the third item. Again, its weight is more than the capacity. We cannot keep this in the knapsack. Let's try the fourth item in the order. Again, we cannot keep this item in the knapsack. The last item has a weight of 1, which is equal to the remaining capacity of the knapsack. We can keep this item in the knapsack. Knapsack is full now. If we consider the original problem, this greedy approach based on value keeps first item and the last item in the knapsack. However, in this case, we get the value 7 from the knapsack, which is not the optimal one. The optimal solution is when we keep third and fourth items in the knapsack. The optimal value is 8. Let's design the second greedy approach considering weight. This approach has two steps. In the first step, we sort items by weight in ascending order. In the second step, we keep items in the order obtained from the first step until the sum of the weights of the kept items in the knapsack is less than the weight capacity of the knapsack. We have a knapsack, and the weight capacity of the knapsack is 6. There are 5 items. The first item has weight 1 and value 2. The second item has a weight of 4 and a value of 3. The third item has a weight 2 and value 2. The fourth item has a weight of 4 and a value 5. The last item has a weight of 5 and a value of 6. In this approach, weight decides the preference of items. Weight of first item is 1, weight of second item is 4, weight of third item is 2, weight of fourth item is 4, weight of last item is 5. The item with the lowest weight is the first item. It should be given the highest preference. After this, the third item, then the fourth item, then the second item, and the fifth item is at last in the preference. Let's sort the elements in the ascending order of the value. At this stage, we have the items in ascending order based on their weights. Step 1 of the algorithm is complete. Let's consider the first item, an item with the lowest weight. Since its weight is less than the weight capacity of the knapsack, we can keep this item in the knapsack. Now, the weight capacity of the knapsack is 5. Let's try the second item in the order. Since its weight is less than the weight capacity of the knapsack, we can keep this item in the knapsack. Now, the weight capacity of the knapsack is 3. Let's try the third item. Its weight capacity is greater than the capacity. We cannot keep this in the knapsack. Let's try the fourth item in the order. Again, we cannot keep this item in the knapsack. We cannot keep the last item in the knapsack. The knapsack is not full, but we do not have any items left. If we consider the original problem, this greedy approach based on weight keeps the first item and the third item in the knapsack. However, in this case, we get the value 4 from the knapsack, which is not the optimal one. The optimal solution is when we keep the first and fifth items in the knapsack. Let's design the third greedy approach considering the ratio of value and weight. There are two steps in this approach. In the first step, we sort items by the value of the ratio in descending order. We give the highest preference to the item with the highest value per unit of weight. In the second step, we keep items in the order obtained from the first step until the sum of the weights of the kept items in the knapsack is less than the weight capacity of the knapsack. We have a knapsack, and the weight capacity of the knapsack is 6. There are 5 items. The first item has weight 1 and value 2. The second item has a weight 4 and a value of 3. The third item has a weight 2 and value 2. The fourth item has a weight of 4 and a value of 5. The last item has a weight of 5 and a value of 6. In this approach, the ratio of value and weight decides the preference of items. The value of the ratio of the first item is 2. The value of the ratio of the second item is 0.75. The value of the ratio of the third item is 1. The value of the ratio of the fourth item is 1.25. The value of the ratio of last item is 1.2. The item with the highest value of the ratio is the first item. It should be given the highest preference. After this, the fourth item. then the fifth item, then the second item, and the first item is at last in the preference. Let's sort the elements in descending order of the value of ratio. Stage, we have the items in descending order based on their values of ratio. Step 1 of the algorithm is complete. Let's consider the first item, an item with the highest value. Since its weight is less than the weight capacity of the knapsack, we can keep this item in the knapsack. Now the weight capacity of knapsack is 5. Let's try the second item in the order. Since its weight is less than the weight capacity of the knapsack, we keep this item in the knapsack. Now, the weight capacity of the knapsack is 1. Let's try the third item. Its weight is greater than the capacity. We cannot keep this in the knapsack. Let's try the fourth item in the order. Again, we cannot keep this item in the knapsack. The last item has a weight of 4, which is greater than the remaining capacity of the knapsack. We cannot keep this item in the knapsack. The knapsack is not full, but no item remains to be explored. If we consider the original problem, this greedy approach based on the value of ratio keeps the first and fourth items in the knapsack. However, in this case, we get the value 7 from the knapsack, which is not the optimal one. The optimal solution is when we keep the first and last items in the knapsack. So, considering both parameters, we discuss three greedy approaches. In one, we give preference to items with lower weight so that more items can be kept in the knapsack. In the second approach, we consider value and give preference to items with high value so that the most valuable items are kept in the knapsack first. In third approach, we take the ratio of value and weight that calculates how much value we get from each unit of weight for each item. There are two steps in all three approaches. In the first step, we sort items by the weight or value or the ratio. In the second step, we keep items in the order obtained from the first step until the sum of the weights of the kept items in the knapsack is less than the weight capacity of the knapsack. Time complexity of first step is order of n log n because we are doing sorting only, and time complexity of sorting is n log n for n elements. Time complexity of second step is order of n. So time complexity of greedy approaches are order of n log n, which is polynomial. So the exhaustive search method has exponential time complexity, while the greedy approach runs in polynomial time. But does that mean the greedy approach is better than the exhaustive one? The answer is neither yes nor no. Let's understand why. Can we say that the greedy approach always gives the optimal solution for the 0 1 knapsack problem? The answer is no. The greedy method may or may not produce the optimal result. In fact, it's more accurate to say that the greedy approach does not guarantee an optimal solution for the 0 1 knapsack problem. So, if it doesn't guarantee the best solution, why even discuss it? The answer lies in time. The exhaustive search method gives exact or optimal solution. However, it can take hours, days, or even years to finish as the input size grows. For small input sizes, where the computation is manageable, we can safely use the exhaustive approach to get the perfect solution. When absolute accuracy is required and time isn't a concern, the exhaustive search is the right choice. Greedy approach is fast and efficient and gives near optimal solution in polynomial. However, it does not guarantee optimal solution. For large instances where finding the exact solution is impractical, we prefer the greedy approach. When a quick and near optimal solution is good enough, greedy is the way to go. In the next video, we will talk about dynamic programming approach for 0 1 knapsack problem. Thanks for watching. Don't forget to like, share, and subscribe so you never miss what's coming next.